So in this video, we're going to get a lot of practice calculating 3D volumes using the cylindrical shells method. And in a way, this technique is going to be harder because we're going to be visualizing 3D shapes as a bunch of those thin cylindrical shells. So it's a new shape for us, a completely new approach from washers and discs, which are kind of related anyways. But in a way, this shells method is going to be a bit easier because you've seen a lot of the curveballs and traps and tricky things that make discs and washers difficult to use. So we'll go through a whole bunch of shells problems. We'll start with some easy ones, but we'll do all the different kinds of problems with all the possible, traps and tricks that there could be. And hopefully I'll be able to show you that it's all just using that shells method concept that we built up in the last video. So we'll start with this problem, and you know the drill. We want to find the area enclosed by these curves, rotate that area about some line, and find the resulting volume. So y is equal to the cube root of x is basically going to be this. We have y is equal to 0. Just imagine all the points who have y's of 0. X equal to 1, all the points with x coordinates of 1. And here is our enclosed region. And we want to rotate this about the y-axis. And if we take this area and revolve it around this axis, we'll of course form a 3D shape. And that shape should look something like this. Some sort of right-angled bowl. We could put some soup in here. So, let's try to imagine the shape as being made up of a bunch of those cylindrical shells. So here is one of these shells. And our first step of shells method is to form the area of one of those rectangles that we use to rotate about our y-axis to make one of those shells. So we take this orange area and rotate it around our y-axis, a complete 360-degree revolution there, and that would give us one of our very thin cylindrical shells, whose volume is very small, dV. Alright, so on our main graph, here is one of those tiny rectangles. Now, the area of this rectangle, I'll start with my width right here. That's going to be dx. So we have dx. Now, the height of this rectangle is going to be this length right here, which is basically the y-coordinate of this green point. So I'm going to write cube root of x times dx, because this gives me the y. And also, of course, I can't have a y times a dx. We won't be able to perform an integral based on that. Alright, so here is the area of one of our tiny rectangles. And step 2 has us rotating that area around the y-axis by timesing this whole thing by 2 pi r, where r is the radius we're using to rotate that orange rectangle in a circle. So on my model down the bottom left, here is my radius. And on my main graph, here is the radius. And that radius looks to be simply the x-coordinate of that orange rectangle. So, 2 pi r, and we've recognized that r is simply x. Now, some people may be thinking, Jeff, I've watched your videos about washers and discs, and I get how you want the x right here, but doesn't that mean you need an equation to give you the x? Doesn't that mean you need to flip our equation such that we plug in a y and we get an x? And that's a valid point, but we need x to be right here because the rest of our math is x. This is actually going to be a dx integral. So we need this to be just x. So now that we've taken this small orange rectangle and rotated it about the y-axis with 2 pi r, where r is just x, now this whole thing represents the volume of one of our thin cylindrical shells, dV, tiny volume. And of course our last step is that we want to add up all of these thin shell volumes. So for the bounds, let's try to find the first shell, the one at our lower x. Well, that's going to be this one right here. Imagine putting that guy around. That's going to make our very first shell. And the x of that will be 0. So our x lower bound will equal 0. And we'll add. We'll keep adding those cylindrical shells until we get to this last one right here, in which we revolve this area to make that last shell. And that last rectangle that produces that last shell will be at x is equal to 1. So that will be my upper boundary. So that's my completed integral right there. Let's take it over to Math World so we can crunch it. And if we do that math, we'll get 6 pi over 7 for the volume of that shape. Kind of looked like a contemporary bowl that you'd find at IKEA. Alright, next one. Start with my curves. Y is equal to x cubed. It's not too bad. Okay. Y is equal to 8. Now I didn't make my graph big enough. And this is 1 right here. This is y is equal to 1. So, yeah, we'll just pretend that this is y is equal to 8. But in reality, it's going to be way, way up here. And we have x is equal to 0. All the points that have x is equal to 0 as their x coordinates. So here is our enclosed region, which we need to rotate about the x-axis. So if we revolve that area about the x-axis, we're getting that same sideways bowl, but it's sideways now. Alright, so let's envision these thin shells, and they're going to be sideways too. So here's one of them, and hopefully you can imagine the rest. So let's start thinking about our shell process here. In our model here, let's imagine one of those, the rectangle of the shell, and let's imagine, rotating that rectangle around to make one of our shells. Okay, so on our main graph, this right here is going to be one of those small rectangles. So let's form its area. I always start with the width, because that's going to be the differential, either dx or dy. That's going to help me through the rest of my work to decide whether I need things in x or y. So my width right here, that's definitely going to be dy, a little bit of length in the y direction. And this right here is going to be my length. And that length, I notice, is simply the x-coordinate of that green point. So, of course, I can't write x times dy. Because of this dy here, I need this x to be in terms of y. I need the equation in which I put in a y, and it gives me that x. So I'm going to write y to the 1/3. All I'm doing there is look at our equation, and I'm getting x by itself. So I do the cube. I raise both sides to the power of 1/3, which gets me this. Again, same exact equation, which forms the same exact green curve, just in its y form, in terms of y. But this equation's giving me those x's, which are the lengths of my tiny rectangles. So this equation forms the area of one of those tiny rectangles, and now I need to rotate it, revolve it around my x-axis to form one of my thin shells. And I do that by timesing this whole equation that I have right now by 2 pi times r. Now, on my model, my r is going to be this. This is going to be the r of the circle that I used to do the sweeping, the revolution. And on my main graph, that's going to be this right here. And notice that this line right here is just the y-coordinate of this point. So instead of writing 2 pi r, I can write 2 pi y. And now, when I plug in a y into this equation, what I've programmed that math to do is to give me the volume of one of those thin cylindrical shells, dV. And I now want to add up all of these small volumes. Now for the bounds. So let's think about our beginning y, the rectangle at the very first y, because this is a dy integral. Well, that rectangle is going to be basically right here. This is going to be the first rectangle that produces that first shell. And the y-coordinate of this first shell will be 0. And I keep doing this and adding on these shells until I get to this last one right here. And the y-coordinate of this last rectangle that produces that last shell, 8. So that will be my y upper bound. Alright, so let's see the math on this one. So the math for this one gets a little gross, especially here. And we have to do that 8 raised to the 7 over 3 and clean up that math. But it gets you to a final answer of 768 pi over 7. Alright, so hopefully you're noticing how, just like washers and discs, got weird. It'll make you rotate about the x-axis and turn it into a dy integral and make you think in terms of y. These same sort of traps, these same tricky things, are here in shell problems as well. Okay. Alright, let's graph these curves. Now this one looks weird. X and y are on the same side. Well, I'm just going to put it in terms of x, because that's how we're used to. I'm just going to divide x on both sides, and that'll get us y is equal to 1 over x. And I know that is basically going to look like this. Okay, now for the lines. X is equal to 0. All the points that have x's of 0. Y is equal to 1. And y is equal to 3. So our target region is this. And we want to rotate this region around the x-axis. So here's our x-axis. If we take this area and swing it around that x-axis, we'll get this volume. So let's imagine this volume as a bunch of shells side by side. So here's this orange shell created by taking this orange rectangle and revolving it around the y-axis, or the x-axis rather. We also have this blue shell created by this smaller rectangle. So hopefully you are able to imagine those shells. So let's start our process here. Here's one of my rectangles I want to rotate. Let's write its area. I always start with the width, the shorter side of that rectangle. This is going to be dy. And this right here is going to be our length. And our length is an x-coordinate. So I need an equation that gives me the x-coordinates of these green points. So I've got to take this equation right here and put it in terms of y. So I plug in a y, do some math, and it gives me an x. And that's going to be x is equal to 1 over y. So 1 over y gives me the x's, aka the lengths, of all my orange rectangles. And I times it by dy, which will be the width of each one of my orange rectangles. So here is the area of the tiny differential rectangle that I want to rotate about the x-axis. And of course, to rotate it, I times this whole thing by 2 pi r. So let's find this r that we're using to swing that rectangle around the x-axis. So my model, here it is for the orange. And on my graph, here it is. So this red line looks to be the y-coordinate of this green point right here. So 2 pi y should do it. And again, there's potential for some confusion right here. Why am I not taking this y and putting it in terms of x? Why am I not writing this? Because, this equation does give me the y's. Well, this equation here is in terms of x, and the integral that I've built so far is in terms of y. So I'm absolutely fine just putting y here. I just want those y coordinates. And in this case, just slapping y right there is fine. That may feel weird, so I just want to make sure I really address this. So 2 pi r is y, and times 1 over y times dy, that'll give me the complete volume of one of our very thin cylindrical shells, dv. And now I want to add up all of these shell volumes. Now, this is a dy integral. What's going to be the rectangle at our lowest y? What's going to produce that very first shell? Well, this rectangle right here is the one at our lowest y. So it's going to produce the very first shell. And the y-coordinate of that very first rectangle is going to be 1 right here. So y lower will equal 1. And I'll keep adding all of these shells that these rectangles produce until I hit this one right here, which is at y is equal to 3. So that will be my upper bounds. Alright, let's do the math. And actually this math is so easy, we don't even have to bring it into the math dimension. If I do y times 1 over y, well, that just cancels out to be 1. I mean, of course I can bring my 2 pi out, so I have 2 pi dy, our bounds 1 to 3. What's the antiderivative of 1? dy, well, that's just going to be y, evaluated lower at 1, upper at 3, times 2 pi. That'll be, if I evaluate at the upper bound, that's just 3, minus evaluating at the lower bound, that's just 1, all multiplied by 2 pi. That's just going to be 4 pi right there. My answer. That's interesting. Let's do another one. So for this one, we actually have 2 curves rather than, one curve and then just a whole bunch of lines like we're used to. So you know that this is going to get interesting. You have our basic parabola. Alright, then we got this. Well, that's going to be fun to graph, but just graph its points of interest first. We know it's going to be some sort of concave down parabola. But because of this 6x here, it's not going to be, right on the y-axis. It's going to be somewhere It's going to be somewhere over here, or maybe over there, something like that. So let's figure out the intercepts, the x-intercepts, where y is equal to 0. And help me figure out what x's cause this purple equation's y to equal 0. I'm just going to write it in this form. I'm going to factor out our x. So we know that x is 0 will cause our entire equation to equal 0. So here is where one of our intercepts is going to be, one of our roots. Now what will make this whole binomial equal to 0, so I can make my entire equation equal to 0? Well, that x will be 3. So I know that when x is 3, y is equal to 0. Well, you know what? It's going to look something like this. And I know that our max point right here is going to be right in the middle. Parabolas are symmetrical. So I'm pretty confident that this x right here is going to be perfectly splitting this interval from 0 to 3. I mean, I'm betting this is going to be 1.5. I have no idea what this height will be, but how about we just find it? Let's just apply our Calc 1 and figure out what this local max is. It may be useful, it may not, but let's just do it anyways. So I'm going to take the derivative of this equation. I'm going to look at this form for the derivative rather than this one. I don't want to do product rule. If I do that, I will get 6 minus 4x. Okay, so we want to set our derivative equal to 0. And therefore, if I do my algebra here, move 4x over to the left equal to 6, x will equal 6 over 4, which is just 1.5. Okay, and when x is equal to 1.5, our y is equal to, if you plug that 1.5 into this equation, what will we get? We're going to get 4.5. Unfortunately, my graph only has up to 3. So let me just erase that. And let's just call this height here 4.5. I'm definitely going to want to find this intersection point. So let's ask the question, what x's will cause both of these y's to equal each other? So let's set the green y equal to the purple y. And let's see what the math tells us. Let's follow the algebra. If I move that negative 2x squared from the right to the left by adding 2x squared to both sides, I'll get 3x squared. And I'll subtract 6x from both sides to move the 6x from the right to the left. So I'll get this. Alright, what x's make this equation equal to 0? Well, let me factor out an x. Well, apparently 0 will. And that's actually right here. There's one of our intersection points. Now, what x will cause this binomial equal to 0? That will be x is equal to 2. So, definitely doesn't look like I've drawn this graph well. So this x will be 2. And actually what we learned earlier was this x was 1.5, which is impossible. I really drew my graph badly. What my math is telling me right now is that my intersection at x equal to 2 will actually be to the right of this maximum here instead of to the left of it. So let me just make my graph look a little more realistic here. So I move this over here. So the x of this intersection will be 2. And our enclosed region will be this one right here. It was a bit messy, but this stuff happens. I'm going to take this area and rotate it about the y-axis. Alright, so let me just erase all this math and all these parts of the graph that we don't need. Alright, so if I take this region right here and send it sweep it around the y-axis, which will get us this shape. I think I'm getting better at drawing these 3D things here. Probably the weirdest bowl we've seen. Alright, so let's imagine the shells. So here's one of our shells, and we can imagine the rectangle that we rotate about the y-axis to create this thin shell. So we'll start doing our steps here. Let's locate one of those small rectangles in our graph. Here it is right here. Okay, it looks like the width is going to be dx, small distance in the x direction. Now, the height is going to be this height right here in blue. Now, notice how that is not the purple y-coordinates or the green y-coordinates. So what is it then? This is where shells gets tricky, just like washers and discs got tricky. How do we form that blue length of that orange rectangle? Let's take the y-coordinate of this point and subtract off of it the y-coordinate of that green point. So, how do we get the length? Well, we take our purple y's and subtract off of it our green y's. And take this and multiply it by the width of a rectangle dx. But as we see here, we've got to make this whole thing be in terms of x. So I'll write 6x minus 2x squared, because that equation gives me those purple y's minus x squared, because that equation gives me the green y's. And this whole thing, of course, multiplied by dx. And again, you want to make sure your equation that you formed works at all points in your area. So if I take my purple y right here, that this equation gives me, and subtract off the green y that this equation gives me, I will get this orange line, which will be the length of my rectangle. Got it. And of course, if I multiply this by dx, multiplying by the width, I'll get the full area of this little rectangle. So, ideally, you want to test your equation at a couple points, just to make sure it holds. And now that we know this is the correct equation that gives us the areas of these tiny rectangles we want to rotate about, now we can go ahead and take that little area and rotate it about our y-axis. And we do that by multiplying this area by 2 pi r. And the r that we're using to swing this orange rectangle around that y-axis is this r. And it looks like this radius is simply going to be whatever the x-coordinate of the rectangle is. So instead of r, I can just write x. And it's okay just to write x because the rest of our equation that we built up is in terms of x. This is officially a dx integral. So now my equation gives me the volume of one of our very thin cylindrical shells, and now I want to add up all of these small shell volumes. So for our bounds, our first little rectangle at the lowest x is going to be right here. We'll rotate this guy around to create our first shell. And the x of that rectangle is 0. So that's our lower bound. We'll keep adding these shells that each of these rectangles creates until we get to this tiny one over here. That'll be our last shell, and that'll be located at x is equal to 2. So there's our upper bound. And there we go. The integral is complete. Let's do the math. And if you carry out that math, you'll get a nice number of 8 pi as that volume. Okay, moving on. Alright. Let's start by graphing this curve. Definitely going to be some sort of concave down parabola because of that negative in front of the x squared. So let's figure out some points of interest to figure out exactly what it is. I might start with what x's cause y to equal 0. Let's figure out those x-intercepts. I can factor out an x. So I know that x equals 0 will make this whole equation equal to 0. And also x equals 4 will make this guy equal to 0, and thus the whole entire equation equal to 0. So those are my x-intercepts right there. x0, y0, and 1, 2, 3, 4, x4, y0. So parabolas are symmetrical, so it's going to be something like this. Why don't we figure out what that maximum is, just so we know? Let me calculate the derivative of this equation. 4 minus 2x. Okay, what x's cause us to have a horizontal tangent line? X has to be 2. So our max will occur right here. No surprise. Let's just figure out what that max y is. Let's plug x equal to 2 back into our equation here. So at x equals 2, y equals, let's do that math, is 4. So 1, 2, 3, 4 right here. So there is my concave down parabola. Got the standard issue line here. Y is equal to 3. All the points for which y equals 3. So my enclosed area is this tiny blip right here. And we want to rotate it about the x is equal to 1 line. So all the points for which x equals 1. So I'm really going to want to know what these two intersection points are. There's a chance that's going to be important. Also, what if I messed up my graph again? What if this whole x equals 1 thing is actually to the right of this intersection point right here? Something like what happened in our last problem. So let's just go ahead, find out those intersection points. So because of our y is equal to 3 right here, I know the y coordinates of both these points is going to be 3. So how about we plug in 3 into y and see what x's come out? And you know what's interesting? 2 x's should be coming out. Let's see how the math deals with that. So 3 is equal to 4x minus x squared. Well, this just turns into a quadratic equation. Let me make this a quadratic equation that equals 0. So I'm going to move the x squared over on the left to make it positive, and I'll move this 4x to the left as well. Let's get everything on one side. So x squared minus 4x plus 3 all equal to 0. So this is my basic quadratic form right here. A is 1, B is negative 4, C is 3. So let's use our quadratic formula. So if I do my quadratic equation, of course I'm going to get 2 values for x. And those values will be x equals 3 and x equals 1. Those are the two numbers, 3 and 1, that will make this whole equation equal to 0. And of course what that means for us is that these two x's are the x-coordinates of our two intersection points. Looking at the one on the right, I see that my graph was almost spot on. This is x 1, 2, and 3. Now this intersection point could be moved a little bit to the left. We can see that that yellow dot there is not quite at x is equal to 1, so let me just change my graph real quick. So there we are there. So now that I've finally graphed this green curve, I can proceed with my problem. So I want to rotate this area about the x is equal to 1 line. And that will create this shape. Okay, so let's imagine some shells. Okay, so on our model, here is one of the rectangles that we would sweep across that axis to create one of our thin cylindrical shells. So we'll start with our shell technique. On our main graph, here is one of those tiny rectangles. So its width will be dx. And it looks like its length will be the difference between the green y-coordinates and my purple y-coordinates. It looks like it'll work in all cases. Same thing for this blue rectangle. The length of this rectangle will be the green y-coordinate minus the purple y-coordinate. That'll get you the length. Alright, so green y's minus the purple y's will get us the length of our rectangle, which we want to multiply by the width of all those rectangles. Each one will be dx. And of course I just can't leave these as y's. I gotta write the equation in terms of x. That gives me those y's. So for the green, that's just going to be 4x minus x squared. Minus, well, what gives us those purple y's? Well, it looks like each one of the purple y's is just 3. So as simple as that. All multiplied by dx. So this gives me the area of each one of our small rectangles. Now I have to rotate these rectangles around my x equal to 1 axis. Which means, to do that, I have to multiply it by that circumference, 2 pi r. Alright, so let's envision our r. On our model, here it is. From the rectangle to my x equal to 1 axis. On my graph, here it is. Now, notice how this radius is not simply the x-coordinate of this point right here. We've been very used to having the radii be very easy. 2 pi x or 2 pi y. Not in this case. So how do we form that red radius there? So just like, when those washer and discs method problems got kind of tricky, we had to bring that subtraction or addition together to make those radii. Exact same thing here. So hopefully you all are comfortable with that technique. Alright, let me draw this radius in blue here. So here is the radius we need to use to sweep that orange rectangle around that x is equal to 1 axis. Let's form it. Well, how about let's take the x-coordinate of this rectangle in green and subtract off of it this length right here. And that length is 1. So I'm thinking that for r, the math that will give us the r in all the cases of all those little rectangles will be x minus 1. Let's test it in one more spot just to make sure. Alright, let's consider this smaller rectangle right here. So I'll start off with x, the x-coordinate of that orange rectangle. Here it is. Don't forget what those x and y's mean. And we want to subtract off of that 1. And 1 is always going to be the distance to this x equal to 1 set of points. And it looks like if we do that subtraction, we're left with this length here. There we go. It worked there. I'm going to assume our x equal x minus 1 approach works everywhere. Alright, so it looks like this big equation gives us the volume of one of those thin cylindrical discs. And of course, we want to add up all of these volumes. So this is a dx integral. What is the rectangle at the smallest x? Well, it's going to be this one right here at x equal to 1. That'll be my lower bound. And I'll keep adding up those cylindrical shells produced by these super skinny rectangles until we get to this last one right here. And what is the x of that rectangle? Well, x is equal to 3. So that will be my upper bound. So just like in washers and discs, these problems get more complicated when we're rotating about lines that are not the x or y axes. So just watch out. They'll kind of tip you off. If you see rotate about something that's not the x or y axis, you know finding that radius is going to get a tad bit complicated. You're going to have to form that radius with a little bit of addition or subtraction. Alright, so let's crunch this integral. And doing this integral is definitely annoying, but we'll get 8 pi over 3. This one looks easy. These curves don't look too bad. But watch out, we're rotating it about neither the x nor the y axis. Be careful. We'll start with this one. That's your standard y is equal to x cubed graph. Y is equal to 0. All the points that have y's of 0. X is 1. All these points right here. Of course, this intersection point here will be x is 1, y is 1. And our enclosed region will be this right here. And we are to rotate this region about the y is equal to 1 line. So if I take this area and rotate it about the y is equal to 1 line, I'll get this shape right here. Alright, so we want to start our shell's approach. Let me imagine one of our shells. And I can imagine one of those small rectangles that I use to form one of the shells. And on our main graph, this might be one of them right here. Alright. So let's form the area. So my width will be dy, a tiny bit of y distance. And the length will be this blue line right here. We have to be careful. This blue length is neither the x coordinates of the green nor the x coordinates of the purple. It's going to be some subtraction between those x's. So the first thing I want to do is put our green curve and our purple curve here in terms of y so that it gives us the x coordinates. I'll do my green curve. I just have to raise both sides to the power of 1/3, and that will get me this. And for that x equal to 1 curve there, I mean, there's really nothing to do. I mean, all these points on this purple line here are at an x coordinate of 1, so we really already have the x's of those purple points. So to find that blue length of that rectangle, I bet I can take my purple x right here, which is just of length 1, and subtract off of it the x of my green point. Yeah, that'll definitely give me this remainder, this blue length. Alright, so I'm going to put that out there. I'm going to say 1 minus the x's coming out of that green equation. But I'm putting it in terms of y so that it gives me the x's. And of course, I'm doing that because the width is dy. I might just test this equation in one more spot just to make sure it works. Maybe for this tiny rectangle right here, I'm going to do 1 this length minus the x-coordinate of this green point right here that y to the 1/3 is giving us. And yes, looks like it's going to work again. My remainder of that subtraction is going to be that blue length, the length of my rectangle. So that'll do it. So my equation that I've built so far is giving me the area of each one of those tiny rectangles. Now I have to times by 2 pi r. So I can rotate that rectangle around to get my shell. Of course, 2 pi r. Let's see what that r is. On my model, my r is this length. On my graph, it is this length right here. It's a vertical line, so it's going to be something, it's going to be y, because y's are vertical lengths and x's, or things in terms of x, are horizontal lengths. So I bet I can do 1 right here minus the y-coordinate of the green point. So I'll write that out. 1 minus the y-coordinate of points along that green curve. Okay, so let's try that again for a different rectangle. Alright, so here's another rectangle. The r that I'll use to swing it will be this one. Alright, so let me try my equation. Let me try 1, and let me subtract off that the y-coordinate. And sure enough, yes, my little remainder will be this blue length right here. So it looks like I've crafted that r. So that will be my radius. So I've completed crafting one of my small cylindrical volumes, and I want to add up all these volumes. So this is my dy integral. What's the rectangle at my first y, my lowest y? Well, this will be it right here, this very, very long one. So y lower will be 0. And I'll keep adding in those shells until I reach this final rectangle right here, which is at y is equal to 1. Alright, so we'll do the math on this integral, and that'll get us 5 pi over 14. So shells is hard enough, envisioning that, and it gets even harder when we have to think in terms of y, and we have to, craft the radius ourselves. This is a perfect example of how hard, sort of twisted, these volume problems can be. So again, I always say, don't just follow the formula that the professor gives you. Think slowly and use those steps and piece and build that integral together, and you'll be able to dodge all the curveballs that your professor could ever throw at you. Okay, we'll do one more. Alright, only 2 curves for this one. Our basic parabola. And we have a concave down parabola that's shifted up 2. I know it doesn't look like it, but let's just call this 2 up here. I messed up my graph scale again. So let's figure out where these intersection points are. And to do that, I'll set both of these y's equal to each other. So therefore the whole equations will be equal to each other. So x squared is equal to 2 minus x. I'll add x squared to both sides of my equation to move it to the left. That'll get me 2x squared is equal to 2. Divide by 2, x squared is equal to 1. And therefore x will equal plus 1 and minus 1. So if I plug -1 and 1 into either one of my equations, my y will be 1. So here are my intersection points. My enclosed area is right here. And we want to rotate this area about the x is equal to 1 line. If I take this region, swing it around that line to produce a 3D object. Okay, let's bring in one of our shells. And here is the area that we use to create that shell. On our main graph, here is maybe one of those small rectangles. Alright, let's get into our steps. Form an equation for the area of one of these guys. Width first, dx. Now the length, the height, in blue right here, we're going to form that using a subtraction. I can see to form that blue, it's going to be this purple y right here minus the green y. So purple y minus green y gets me the height of that rectangle times dx, the width, to give me that area. And I might try this one more time for another one. Maybe this one out here. So purple y, okay. Subtract off of that the green y. And what am I left with? I'm left with this remainder. Alright, that's working. Correct approach, but of course I need both of these y's in terms of x, because this is going to be a dx integral. So the equation that gives me those purple y's, 2 minus x squared, minus, where's the equation that gives me those green y's, x squared, whole thing getting multiplied by dx. Alright, there's our area. Of course, to rotate it about that x equal to 1 line, gotta times this whole thing by 2 pi r. Well, on my main graph, that r will be this distance, so we're gonna have to craft that as well. Well, it's definitely not going to be simply x, because the x of this orange rectangle is this distance. This is the x of my purple and my green point. We can do 1, which is the distance to this x line right here, 1 minus the x coordinate that purple and green line are giving us. That'll work. So instead of 2 pi r, I'm going to do 2 pi 1 minus x. And let's just try that equation one more time for a separate rectangle just to make sure we're getting it. Maybe this rectangle right here. I would swing that rectangle around using this much larger radius. Let's see if our equation holds. So I'm going to take 1, which is going to be this distance right here, and subtract off the x coordinate. Alright, well, our x coordinate of this rectangle is this purple line right here. And notice that this purple line is going to be a negative x. So essentially what we're doing is we're doing 1 minus that negative number that is that x coordinate. So we're subtracting off a negative number, which means we're really adding, which is actually kind of what we need. We need to combine that red length here and this purple length to get us the full blue radius. So a bit scary there, but our equation still holds. And it really all comes down to, remember that x's and y's are just line lengths. And just remember they can be negative too. So now this thing captures one of those thin shells for me. And I want to add all them up. rectangle at my lowest x, my first one is going to be right here at x equal to -1. So -1. And I'll keep adding those shells on until I reach this one right here at x is equal to +1. Okay, so let's math it out. And if we do that math, we'll get 16 pi over 3. Hope this video helped you to get some good practice using the shells method of volume calculation. I always recommend, when you're practicing for the first time, take it slow. Really focus on each step and those line lengths and all that good stuff. And as you practice, you'll get faster and faster doing this. So best of luck to you, and I'll see you in the next one.